Alright, so now we're still trying to solve a second order linear homogeneous differential equation with constant coefficients. In any case, we need to write down the corresponding characteristic equation, and we have covered the case of the positive discriminant of the characteristic equation and of the negative discriminant of the characteristic equation. But we don't know yet what to do if the discriminant is 0, right? So here is an example of this. Now, if the discriminant is 0, it means that the characteristic equation is the complete square, right? So in this case, AR square plus BR plus C is in fact is A times R minus B over 2A squared. I hope I'm right. Yeah, I think I'm right. Well, and we have a repeated root. Well, but then if R is that repeated root, so which means B over 2A, then e to the RT is still a solution, right? But theoretically we know that there must be two linearly independent solutions. So where do we get the other one? So we know one of them, so how do we construct the other one? And of course I could just tell you the right answer, but it is much more interesting and much more useful for your learning is to go through this kind of method step by step, right? So in order to see how it was obtained. The reason is because similar ideas, but in a much more complicated way, are going to appear later in today's lecture and in the method of variation of parameters. So here is what we are going to do, right? So we are going to look for a solution in this form, where y equals some unknown function times the e to the rt. So let me try to see what's going to happen. And so I'm going to write that y equals v times e to the rt, meaning that v is a function of t. Then what is y prime? So y prime is v prime e to the rt plus rv e to the rt. So y double prime. Now I need to differentiate this again. So is v double prime times e to the rt plus v prime times r e to the rt plus rv prime e to the rt plus r square v e to the rt. Wow. Okay, that's a lot to deal with, I guess. And now we need to substitute it to the original differential equation, right? So which means that well, maybe let me simplify it a little bit. So note that these two terms are exactly the same, so I can just write 2 here, and I will write e to the rt here. Okay, so now when we are substituted into the differential equation, the term a double prime should be multiplied by a y prime should be multiplied by b, and y multiplied by c. So let us do it. And notice that this whole thing is multiplied by e to the rt. So we are going to take it out. So e to the rt times now the left hand side of the differential equation. I'm going to have a v double prime plus 2 you know what, let me do it differently. So let me combine all terms with v double prime first. That there is just one term with v double prime plus, let me combine all terms with v prime. And so v prime, we have b from y prime and plus 2 r times a from y double prime. Okay, so how many terms with v do we have? So with v we have cy plus b c plus b r plus a r square times v. Okay, right? But now notice that this is our characteristic equation. A r square plus b r plus c equals 0. So which means that this is just 0. Alright, now let's look at this. B plus 2ra, but notice that r equals b over 2a. So let me write it. So r equals b over 2a, which means that this part is 0 too. Right, so what we get is that a y double prime plus b y prime plus c y is just this a e to the rt v double prime, and it should be 0. So what we get is that v double prime is 0, and if the second derivative of an unknown function is 0, it means that this unknown function is just a linear function, c1 t plus c2. So which means y equals c1 t plus c2 times e to the rt. So c1 t e to the rt plus c2 e to the rt. Alright, is it all? Well, it seems like the general solution, but in order to make sure that it works out, we also need to verify that the Wronskian of these two functions is not 0. So let me do it. So let me find the Wronskian of these two solutions, just to make sure that it works out. So the Wronskian of t e to the rt and e to the rt is the following determinant. So the first row is just the functions, and the second row are their derivatives. So the derivative of t times e to the rt is e to the rt plus rt e to the rt, and here I have r e to the rt. Okay. Now I can take out e to the rt twice from both rows, so it is e to the 2rt times. Then when I multiply like this, I get tr minus, when I multiply like this, minus 1 minus tr, and this is minus e to the 2rt, which is non-zero, so they are linearly independent. Okay, done. So here is an example. And so when we write down the characteristic equation, minus 10r plus 25, this is a complete square. And so the discriminant of a quadratic function is 0 if and only if the function is a complete square. So both roots are 5. So the general solution is just c1t e to the 5t plus c2 e to the 5t. Okay, um, here is the general theorem. I mean, we already proved it using this kind of method with multiplying by an unknown function v. Well, and finally, a little challenge for you. So we have covered these three cases: two different real roots of the characteristic equation, a multiple real root of the characteristic equation, and two different complex roots. But how do we solve the second order linear homogeneous equation with constant coefficients if the corresponding characteristic equation has a repeated complex root, right? So that's